Welcome back, class, to week number 9 of Intro to Data Science. It's great to see you here on Zoom this time. My apologies for not being able to make it to our in-person class last evening. As I indicated on my Canvas announcement, I did become ill, which kind of surprised me. I thought that I had developed a superhuman immune system, and in that I hadn't been sick for over 4 years. But I guess in reality, it was just observing pandemic protocols that helped me avoid getting sick. It's very inconvenient being sick. I don't think I'll do that again. So anyway, as promised, I am recording our lecture on machine learning for this week on Zoom. So the recording for tonight's lecture will be available soon after the presentation ends. And the agenda for tonight is actually half of the machine learning lecture. So I'm just going to be doing our usual preliminaries and tip section part of the class, and then I will go over the entirety of the slides for week 9, and that's it for this segment of week 9. So there's a lot of slides for this week, at most of any lecture. So it's kind of like a mini lecture in and of itself. So I thought I'd break it up this way, kind of save my voice anyway, and get that done tonight, all the slides. And then at some later point, I'm thinking probably tomorrow, I will record the balance of the lecture, which is it will just be on the R code, of which there's a lot of R code. So there's a lot of material, a lot of content for this topic, and there's good reason. There's a lot of good positive material that we need to cover in order to sort of propel you to the point where you can actually do a reasonable amount of data science based on what you've learned thus far. So, okay, so I see we have a couple of attendees for tonight. I thank you for tuning in. And just to repeat, this lecture will probably go around an hour and a half with no break. So I'm just going to be doing the intro and the slides, the tip section and the slides, and then I'll do another recording with just the R code, probably tomorrow. So anyway, welcome back. So that's the agenda tonight, is to cover the preliminary parts of machine learning, and the slides are actually going to put you in a good place for understanding what sort of the goal of data science is and how machine learning allows you to realize that goal. So it's an important part of the whole process, and that's why I have this slide back up on the screen here. And the slide is from week 1, of course. And just to give you a feel for where we are right now, we've sort of marched along with the boxes, and we're at this box, machine learning box here tonight, which is the segue from all the hard work that we've done up to this point into actually getting something done with making predictions. And that box that we're looking at here is also coupled with the next box, which is model evaluation. And so those two go hand in hand. They're very important, where you do a machine learning experiment, and then you check the results of the experiment, and you decide whether the results are satisfactory, and then you move on or not. If not, then you have to backtrack in the data science process a number of boxes, hopefully not too far back, and you'll strategize different approaches and give it another try. So yeah, data science is an iterative process. It doesn't always work the first time, and so you just have to be creative into knowing when it doesn't work the first time what you can do to improve the situation. So at this point, we're entering into machine learning, and so the supposition here is that you have a filled feature vector. You've made the decisions along the way by getting to know your data set well, and so now you have a good feeling for what useful feature variables, predictors will be for your machine learning algorithm. Now, that feeling is kind of subjective, and you've done as much work as you can up to this point in coming to that decision, but it may not be ultimately the final decision. So that's where we are right now, is in this part of the data science process. Okay, so let's see. Let's close this. Okay, so what I want to do is start off with some preliminaries, as I normally do. So the reading for this week and next is, well, actually, no, just for this week, there's a lot of reading. Okay, so the textbook will help you out in a number of areas. So chapter 5 on regression methods will be one of the topics we talk about this week. And then chapter 6 on classification methods is another area. And then chapter 7 on model performance is the final area for the reading. Let's see. And then just a reminder, I know it's sort of after the fact, but the suggested due date for the homework number 2 was last night at midnight. Suggested, meaning you can still hand it in up until March 21st, but this was the suggested due date. And even though Canvas might say that you're late, if you try to hand it in after, well, actually now or moving forward, don't worry about it. You're not graded off on lateness or anything like that. It's just, I didn't want you to get backed up. So that's why I had the suggested due dates. And then also last week, we released homework number 3, which will make a lot more sense now after these lectures, so that you can get started on that. Homework number 3 is only 3 questions instead of the normally 10 questions. There's a regression problem, there's a classification problem, and there's a clustering problem. So those 3 problems will make up homework number 3. So anyway, you will be able to complete homework 3, well, the first 2 questions after this segment, lecture, or class 9, number 9. And then the final question on homework 3 you'll be able to do after next week's lecture, so next Tuesday. Then you'll be able to complete that. But it's great if you like sort of get in front of this stuff and try to solve the problems as we cover the material in class. And also after tonight's or this number 9 lecture, you'll be able to pretty much do everything you need to do for the class project. So that's good. You have ample time to complete that. Okay, so let's see, what else do we have? Our vendor of the week. So vendor of the week is these, here we go, Domino. So Domino Data Lab is our vendor of the week because it matches our theme for tonight of machine learning. So Domino made a name for itself by providing solutions for data scientists to use in terms of producing scalable machine learning solutions. So that generally these products that they make available are for enterprise class deployments of machine learning. These are deployments in big companies. And so they have something called an ML Ops platform. And ML Ops means just machine learning operations. So these are tools that you purchase, the commercial products, so that you can monitor the data pipelines. You can monitor the data sources. You can monitor the use of machine learning algorithms and sort of assign metrics to how well they're performing after, let's say, you run a data pipeline. And they have a lot of so-called alerts that they will send out depending on how you've configured the tool. So if the machine learning algorithm isn't running up to par, then it alerts people and you can go and determine what's going on. And so this would be for like mission critical applications of machine learning. These are cases where you need maybe your corporation is their business is based on the successful operation of these machine learning solutions. And so if anything happens, your company is at stake. So you want to make sure that everything is running as you have intended. So that's why these tools, MLOps tools, are so important. So these are for big companies. They brag about 20% of the Fortune 100 companies use Domino Data Lab for their enterprise MLOps solutions. So it's a very respected company. So I suggest you take a look at that video I embedded, get a sense for what they do, and if you're interested, just drill down on their website. Okay, so that's our vendor of the week. And then I also want to, there's a link in the GitHub site in the data science section. And let's see. Yeah, it's right here. It said, what is data science imposter syndrome? That leads you to this article. Okay, so the concept, the psychological concept of imposter syndrome is not limited to data science. It is a well-known phenomenon in many areas of life, business, work, and so forth. And it's kind of like when you are learning a new discipline and you become feeling confident that your knowledge is increasing, your abilities are increasing, and your skill sets are becoming much more full. And all those are great things, right? I hope you're starting to feel that like in this class, especially after the next couple of lectures, you should feel somewhat emboldened that you can start solving real life problems. And so, so that's great, but there is a downside to that. And this is the psychological effect of imposter syndrome is something may happen that triggers a sort of a internal feeling in you that, oh, gee, I don't know as much as I thought I knew. And in fact, I'm feeling like I don't know anything now. And what am I going to do? Have I wasted my time? Oh no. So people feel this way, especially, I guess, in data science, because it is such a fast-paced, accelerated industry. Things are happening so quickly, and you hear news and announcements and research, things like that are just going at a blinding pace, and you start feeling like, how am I going to ever keep up with this? And you start feeling like you're going to doubt yourself, and that, many data scientists feel that way. And so I just want to warn you that you may have something happen that'll trigger this in you. Like maybe you'll read one of those books that I've been recommending to you, or you'll watch some, like conference videos, or you'll attend a meetup group presentation, or you'll read a blog article, or I don't know what. And you might read some of this stuff and not understand anything they're talking about. And then you think, well, what have I been studying this last 10 weeks? Well, here's the thing is it takes a while to really get acclimated in this field. Longer than 10 weeks. Okay, so I'm going to stress next week during our lecture how important it is for you to keep pushing forward and keep moving, taking action on a lot of the recommendations I've been giving you all this quarter, because life as a data scientist means you never stop learning. You can't, otherwise you'll fall behind. And I don't care how advanced you are, you still have to keep learning. I mean, actually that's one of the things I love about this field, is because as a sort of an academic at heart, I love learning, and I never stop reading. I never stop finding new resources, new books, new talks. It excites me. I love that stuff. So maybe that's the best way to combat imposter syndrome in this field is you just keep moving forward, and you won't feel that effect. So I just want to warn you, because I've heard, from past students and so forth, and it's important to give yourself a pep talk. And don't worry about it. You're gonna keep pace. It's just maybe when you feel imposter syndrome, you come back and visit our GitHub site in this class, like months from now, and I'm always updating it. And there's a fresh set of resources for you to keep learning. So just remember that. There's always stuff to read and consume in terms of resources. So anyway, that's my little thing about imposter syndrome. Okay. And then, oh, you know what? There was a couple of things that I just opened up on Canvas today, which you might have interest in. So over on week 9, yeah, there's something called Copilot for R. So this is interesting. This is interesting. It's a tool that was developed and released on GitHub, and there's a way on GitHub where you can enter code and things like that. And Copilot is a generative AI tool that will play code assist it's like your coding alter ego. So as you're typing code, our code, for example, um, it listens to your keystrokes and it will make suggestions as to what you might want to type next. So it's kind of like that feature on cell phones when you're texting, and in Microsoft Word, and other applications where there's this kind of look ahead. Sometimes it's annoying, because it's not guessing right sometimes when with what I'm typing. I have to avoid the suggestions, but in Copilot, it's interesting because it can anticipate like what you want to do based on the comments you type. So you type a comment line, like setting up some code that you're going to type in, and then Copilot will step in and show you some code and say, "Do you mean this?" To the point where it'll actually write full functions for you. And maybe you look at the code and you say, "Yeah, that's a good head start," and then you'll accept some or part of it and move on. Or you might look at the code that it writes and say, that's no good at all, so you just ignore it. But Copilot has been around for a while now, and I guess in a way GitHub was on a leading edge track for generative AI, which we're seeing so much of now with this is a derivative of large language models that I've been talking to you about all quarter. It, instead of writing text, articles or papers or what have you, this is writing code. And the way it works is that the algorithm that is behind Copilot has taken in immense amounts of code from many different sources, and that's how it's coming up with its suggestions for you. So I thought you'd be interested in checking out the little it's an hour-long demo video of a well-known R guru, and you can see how he's interacting with Copilot as he's writing codes. Very, very interesting presentation. So check that out. The other thing I opened up today was this computer vision tool without coding. Okay, so an old colleague of mine from Stanford, Andrew Ng, he runs a company called Landing AI, and they just announced, I think it was today, a new computer vision tool called Lensing AI, which allows you to produce actual computer vision applications without writing any code. So he has like a no code or low code, no code application environment where you can like upload your own images and commingle them with their pre-trained models for computer vision, and you can then train the model with your new data, and then you can make predictions, like image recognition, that type of thing. And it's very interesting twist to this type of work, because up to this point, as far as I know, you want to do a computer vision application, you have to write a lot of code and have a lot of data. So here, this this free to use new tool is looks very promising. I think it might set a new standard for moving forward with some of these large models, deep learning models, because it's for one thing, it's very expensive to train deep learning models, because the amount of data, because of the amount of compute resources that are required. So if you can sort of share that among many users, then you've reduced the cost that's typically associated with this type of work. So again, there's a very short video here where Andrew is talking about this new solution, and there's a link in the Canvas discussion item where you can go and sign up and try this out. So kind of fascinating. I'm telling you, things are happening so fast in this industry, and as they happen, I make a point of sharing them with you. So you are always state of the art while you're in this class. Okay, so that was that. And let's see what else. I also, I know what. I just opened this up on Canvas. So students are always asking me, like, okay, I've taken your class, I feel emboldened and I can solve real problems. What's like a project I can do right after, sort of polish my skills and check my abilities, things like that. So I put together this so-called post-class project. So this is not graded, it's just for you as maybe the next project you do after this class. And I call this open data hacking because it's based on acquiring a data set of your choosing. So this is the kind of thing where you have to choose your own project. You find a data source for a project that you might be interested in. You research it. Maybe it's something, a topic that you have passion for, and you probably have a lot of ideas at this point. And you go out and look for open data from repositories that are out there. And then you go through the whole data science process. Find the data set. You do data munging, transform the data as you see fit. You do EDA and data viz. You select a machine learning algorithm and you try it out, you train it, you test its accuracy, and then if everything is good, then you do a little data storytelling, and you produce like a final report. You get practice writing a data science oriented report. And so the last thing I encourage you to do with this project, and this is a really good head start for all of you, and that is to create your own GitHub repository and publish the results of this post-class project. And that would include all of your R code. That would include the data set or data sets that you used. That would include the final report. And the thing that's good about this is it'll start you along the path towards being a professional data scientist, because every professional data scientist has a GitHub repo to show off their work. And then this is how you sort of climb up on your soapbox and you tell the world, look how skilled I am. Here's all my best work. And it really works. I know for a fact that, many times hiring managers, looking for data scientists, they'll look at your resume and they'll sort of throw it away and they'll go, no, let's go look at their GitHub repo. And that's where I can learn whether this person is really who they say they are. So yeah, it's like a calling card. You do a good job putting together your GitHub repo, and you're going to do well. So this might be the start of your GitHub repo, is this project. Okay, so if you wanted to take a look at some prior projects, let's see. You can go to our GitHub site for class, scroll all the way down to the end, and here is a list of excellent post-class projects examples from past students who took me up on my offer here, and they did, they picked their projects, and they had some really interesting topics. Several sports oriented projects, one having to do with COVID, hotel bookings, Airbnb. So, interesting topics. And then if you click over to their GitHub sites and you look at the materials, it's pretty impressive. So check this out to see how your fellow past students, how much they learn. And that's one of the things you can tell by looking at their project results, is these people learned a lot from this class. And I hope you can learn a lot, just as much from this class, to be able to do work like this. So do check this out and see what is possible. Okay, so that's the class project, post-class project. So, and then here, a couple of books I want to show you at this stage of the game here. So I said a couple of books, my favorites for last. So this is like my favorite book of all time for machine learning. I think it's many data scientists' favorite book. Every data scientist knows about this book. So Elements of Statistical Learning, I call it ESL for short. I've heard my colleagues call this the Bible of machine learning. And it's like the authoritative text for machine learning. It's got a lot of theory. It's got like complete algorithms that are defined for some of our favorite algorithms in machine learning. And it's got a lot of math. And you just have to get up to speed. And this is not something that you would want to pick up after this class. This would be like, maybe if you keep at it and keep learning, maybe like 6 months to a year from now. And this is the kind of book that you never finish reading. So I will find myself like throwing this book in my backpack when I go off someplace I know I might have some idle time, and I can open a chapter and read a couple of sections that I use to refresh my memory of the theory behind different areas of machine learning. But it's all in here. The authors are top-notch. Hastie, Tibshirani, and Friedman are all statistics professors at Stanford. I know them all well. Hastie was my PhD faculty advisor, and this was my first textbook in graduate school. And I got to say, I started feeling imposter syndrome when I cracked open this book, and I go, I don't understand anything. It was all a mystery to me. But over time, you just keep at it, keep reading it, and it starts to make sense. So, um, so that's the first book I wanted to turn you on to. It's a very important book. And the second book is a book that'll allow you to read the first book I just showed you. I said there's a lot of math in there, right? So in order to get up to speed with the math in ESL, this is a good book for doing just that. Now, this is a relatively new book, and it used to be where I recommended a whole series of books to my classes, like maybe a half a dozen books on different mathematical subjects. I said, okay, if you want to get up to speed with the math for machine learning, here's like 6 books you have to read. Well, this book finally came out, and I was delighted because this is one book that you have to read, which will get you up to speed with all the math that you need for understanding machine learning. So it's a very nice book, very well produced. There's some amazing figures, illustrations, graphics in this book. I would highly recommend it. And so between those 2 books, I think you can soar to great feats. And take those books seriously. Now, you can buy those books, hard copies, or you can go down to the end of our GitHub site and see this one here, ESL. This will lead you to a PDF of this book. So you can get it for free. And the same thing with Mathematics for Machine Learning, you can get this for free as a downloadable PDF. So there's no excuses. Just download these 2 guys, and you're set. I mean, you could study these things, for a year, literally. Just going through, I would guess the first would be the mathematics book, and then go to ESL. You spend a good year on that, and it would be a very good use of your time. Oh, and I just heard last week on Twitter, the authors of ISL okay, so this is what you should see when you click that link, and you should be able to download that. There's the book. So I'm not quite sure. I had a question come up in chat about downloading the book. So but as I was saying, the ISL book that I told you about very early on in this class as a great next book to study, because after this class, because it has all of the like machine learning techniques for R, Introduction to Statistical Learning. I just heard from the authors that they're about to release another edition of this book, except all the code is in Python. And I go, oh, that's blowing my mind here, because I mean, I really love this book for R. And if they come out with a Python book, that's even better, because if you read the R book first and you get, set with all the knowledge that you have of R, and then you pick up the Python equivalent, you should have a very easy transition from R to Python. So it just occurred to me that that would be a good way of moving forward. But this this Python version of ISL is not available yet, so stay tuned. It sounds like a sounds like very promising. Okay. So that yeah, that's it. So those are all the tips that I have for you. And now we can go on to the slides. And yeah, I should have mentioned this earlier, but if you do have any comments, there's that chat window for Zoom, and I'll try to monitor it to see if there's any questions as we go. Okay, so our outcome for this week is, as described, we're going to be exploring supervised machine learning for prediction problems. And prediction problems is probably the type of machine learning problem you typically hear about. You know, when people are talking about machine learning or deep learning or AI, just in general, it's usually, well, we've got these high-powered algorithms and we got all this data and we're using it to predict something. And so that's what we're going to be learning in week 9. Week 10 is unsupervised learning, where we're not worried about making predictions. We're worried about knowledge discovery. Okay, so very different types of machine learning. So our outcome this week will be how to use R for performing simple and multiple regression problems using linear regression. So that's like the first type of machine learning algorithm that we will consider. And linear regression, also known as ordinary least squares, OLS, is used for predicting continuous response variables. So what do I mean by continuous? It means that the response variable that you've identified in your data set that you're using for this project is numeric. Okay, so it's a numeric variable. And whenever you're trying to predict a numeric variable, you're going to be using some sort of regression method. And in this case, we'll be learning linear regression. And we'll be seeing two sort of orientations of linear regression. One is simple, one is multiple. And I'll explain shortly what that means. Now, if the response variable that you've identified in your data set is categorical, okay, so not numeric, it's something like a factor variable, for example, then you cannot use regression methods for that. Instead, you use a classification algorithm. So that's the other type of supervised machine learning we will consider. And we'll be looking at two algorithms, two classification algorithms. One is called logistic regression. It's actually a misnomer. It's not really regression. Logistic regression is a way of describing a problem that has a binary categorical variable for a response. So that, you know, the response variable, let's say a factor variable, has only two levels. You know, it's one or the other. And if you have a situation like that, then you use logistic regression, it'll work fine. On the other hand, in a more general sense, you can use an algorithm called random forest for classification problems, but random forest is not limited just to binary response variables. The response variables for random forest could be multi-level, and it works just fine. You can use it for binary too, but you're not limited to that. Okay, so that's what we're going to be covering. And then the objectives is for this week is to employ supervised machine learning using regression and classification methods. And so the first algorithm we will learn is an algorithm called LM for linear models, and that is available in base R. And for logistic regression, it's that classification algorithm. We'll be using GLM algorithm in R, also in base R. And then the final algorithm we'll consider is random forest for doing the multi-class response variable situation. And note that random forest is not in base R. You have to actually open a package to get at that algorithm. We're also going to see how we use what's called a training set with the machine learning algorithm to fit the statistical model. That's sort of the way data scientists talk about this process. They're fitting the model. And they do that in order to obtain what's called coefficients. And these are coefficients, just think of as a numeric vector. So you know what a vector is in R. A numeric vector is, in this sense, it's a numeric coefficients vector that you can then reuse to make predictions. So you train the algorithm to obtain the coefficients, and then this next step here, you use the trained algorithm coupled with something called a test set to measure the performance of the model. Okay, so it's training first and then testing performance second. And then I guess third is once you've sort of reconciled those two, then your algorithm is ready and set to make predictions on brand new data that the algorithm has never seen before. And that's where you kind of get into a gray area. You don't know how well the algorithm is going to react to brand new data it's never seen. And so you hope for the best, that you've done a good job in training and testing the model's accuracy, but you never really know until you turn it loose on brand new data. And then you may have to sort of retreat a little if the accuracy on new data isn't sufficient. Okay, so that's sort of in a nutshell what we're going to be covering. Okay, so some more overview material on supervised machine learning. So as I mentioned, supervised learning is considered the most common type of machine learning. It's typically associated with prediction, where for each observation in your data set consisting of predictor measurements, also known as feature variables, there is an associated response variable. And when you consider all the response variable values in your data set, these are collectively called labels. Okay, so like just thinking about all the data sets we've seen thus far in this class, we've had data sets that were complete in the sense that if we're going to use them for any purpose with machine learning, the labels were already there. They're natively part of the data set. We didn't have to worry about, oh, where are we going to get the labels? But I'm going to talk about that whole subject more in a moment. But labels have to be there. Otherwise, this machine learning thing doesn't work. So I call linear regression the workhorse of supervised learning. So because the method has been around for a very long time in statistics. And now it's widely used today by data scientists. So like years ago, I mean, I remember when I was an undergrad at UCLA and I was taking a mathematical statistics class, and there's a whole chapter in my stats book on ordinary least squares. And I sure didn't call that machine learning back then. And I didn't even think to call it machine learning, but now it's called machine learning because it fits well within this this definition, which I'm going to talk shortly about. But yeah, it's a workhorse because whenever you have a continuous response variable, then that's the technique you use. And so we're going to be looking at both simple and multiple linear regression. So simple is where you have the response variable and one predictor. And then multiple regression is when you have the response variable and more than one predictor. Okay, so you can actually do quite a bit of good work with just one predictor. If the predictor is highly correlated with the response variable, you can do very well with prediction. So we'll see examples of that. Then then classification is also a supervised technique. That's, I would think it's more often associated with this thing called machine learning because of the types of problems that it's able to solve. I mean, it's things that you hear about more often than, you know, predicting a numeric response variable. Things like, you know, predicting categorical response variables. So this, for example, if it's a like binary categorical response, let's say you're trying to, you're running a subscription business. And so in any kind of subscription business from month to month is worried about customer churn, where, you know, like what percentage of your customers will not continue their subscription next month. So churn is a bad thing. You don't want customers to churn. You want to have them keep paying you their subscription fee, right? So turns out machine learning can do a very good job with predicting customer churn. And so the response variable that you try to predict is customer will churn or customer will not churn. It's a binary situation. Okay. Another good example of that is when you are receiving emails, and you know how you frequently get so-called spam emails, and you hopefully have a good spam filter so that spam emails are automatically put in your spam folder and they don't clutter up your inbox. Well, I don't know if you've ever wondered how that happens. It happens using machine learning, because you know how I don't know if, depending on the email application you use, but if you get stuff in your inbox that is junk. Now, most people, they see junk in their inbox, they just delete, delete, delete. I don't do that because I want to help train the algorithm to recognize spam. So I will like select an email that I know is junk, and I'll click on the spam button. And that means the algorithm is now labeled that email as spam email. So by clicking on that button, I'm helping label the data set that will then in the future be used to train the spam filter, and hopefully will avoid me seeing emails like this in the future. So you're actually taking a moment to classify this email and help train the algorithm, but it helps you in the future too, because you'll get fewer spam in your inbox. So that's a good example of a binary classifier. Spam, not spam. So you could use logistic regression for that, for example. Sometimes the things you're trying to classify are not like tabular data, enterprise data, that type of thing. Sometimes the things that you're trying to classify are images. So images are data. Remember in week 5, we discussed that there's all sorts of unstructured forms of data, like images, videos, audio, stuff like that. And so using images as an example, an image is just a collection of pixels. And a pixel is has attributes like color and intensity. And when you view all these pictures in a matrix, and your eyes gaze over these images, and you recognize them as some object that the image is of, and so a good example of a classifier that uses images, and this is like the very, very first one that anybody thought of using with images, is to identify an image is a cat or not cat. And so how would you train an algorithm to recognize cats? Well, you basically have a lot of images, and some are of cats and some of other things, other animals maybe, and you have to have some process to label these images as cat or not cat. And usually humans are really good at doing that. Humans are very good image recognition devices, the human brain. And so that's how some of these data sets were labeled. It's just they would have people look at these images and classify them, label the data sets. Okay. So it can be difficult to obtain a quality labeled data set. So sometimes you have to rely on what are called natural labels. So that's what I was alluding to when I said, in our class data sets that we use, all the data sets are labeled because you can identify a response variable, and there's values in every single row for that variable, and that's great. That's like natural labels. They appear in the data set, like a data set for like a real estate data set with about homes, home properties, single family homes, whatever. One of the variables might be called home price, and maybe that's the thing that you're trying to predict. And so if you look at this data set, there should be home prices like for every row. Otherwise, like, what's the point? So that's a natural label. Sometimes data sets have to be hand labeled. So sometimes, like in my consulting work, I will come across people who, they say, oh, we've got this great project. And I say, yeah, it sounds wonderful. But they look deep after our discussions. They find they don't have the data set that's required, or maybe they have the data set, but the data set isn't labeled. And so the thing they're trying to predict, it's not possible because there's no labeled data set. So what do you do? Um, it's a long, arduous process of hand labeling data sets. Very expensive too. So, I mean, the email applications have us users label their data sets for free. Well, not everybody does it. I just told you that I do it, but I do it for a selfish reason. I know that the more I help train it, the more it's going to rid me of spam emails in the future. But I'm still, making an effort. A lot of people don't make an effort, and so, all of that, realization of a spam email goes, flying out the door. It's not captured by any process. Okay, then I mentioned data labeling services like Amazon Mechanical Turk, where people are paid piecework to label data sets. And also there are a number of startup companies that have unique perspectives on products that might help in data labeling. I think there's like maybe a dozen such companies in my database right now, and they're working hard to come up with solutions to help label data sets. So it's a big problem in data science, because you can't do anything without a labeled data set. It doesn't work. Okay. So in order to perform any sort of supervised machine learning, a data scientist must take the data set that they intend to use and split the data into two pieces. One's called the training set, the other is called the test set. The training set is always larger of the two. So the idea is where the rows in, let's say, the data frame that you're using for the project are randomly selected to be placed in the training set and the test set. So there's a randomization process. I mean, I guess if you know for certain that there's no implied order to the data set, then you don't have to do this randomization. But I mean, you just select, the first 70, let's say, percent of the rows and put in the training set, and the next 30% in the test set. But generally speaking, it doesn't hurt to randomize it. So the way I'm going to show you to do it in class, it's always going to have that randomization part. And then it's sort of up for debate what the optimal split between training and test is. I just mentioned 70-30, but there's people who use 60-40, 75-25, 80-20. I mean, you could try different splits to see how it might affect the accuracy of the algorithm down the road. It's worth trying to see if a different split improves the situation. But generally in this class, we'll use 70-30. Okay, so the training set portion of your data set is used to train the machine learning algorithm, also known as fitting the model, in order to obtain the model coefficients, that numeric vector of values that constitute these coefficients. Coefficients is like a mathematical term of different values in an equation that sort of act as weights in the equation, but I'll show you that in a moment. The test set, on the other hand, is used to check the accuracy of the algorithm by comparing the actual response variable values that are found in the test set versus the predicted response variable values that are provided through the trained algorithm. Okay, so envision this where you have a data frame in R. And let's say by this point in the process, there's no missing data. You open it up and it looks like, perfectly solid data values. And you look at your response variable and the whole column is filled. You look at all the other columns and they're filled with predictor values. Okay, so by splitting the data set in half, not in half, but into pieces, the large half is for the training set. This will be used to train the algorithm and obtain the coefficients. To test the accuracy is you're going to use those coefficients along with the trained model and make predictions for the response variables in the test set. Okay, so you'll have a group of predicted response variable values for the test set. But you also have a whole set of actual values for the response variable that are in the test set. So your job is to compare the actual versus predicted and see how close it is. If it's really close, then that means your algorithm is highly predictive. And if it's really off, then you have more work to do. This is not working. Okay, so this is a critical concept for machine learning. So let's go over it again. So a critical element of supervised machine learning is defining the training set and the test set for use by the algorithm. The separation of your data set into a training portion and a test portion is the way the algorithm learns. You split up your data set containing actual response variable values into two pieces. The training set is used to train the algorithm by calculating the coefficients. Then use the trained model on the test set to predict the response variable values. So now you have both actual and predicted. So the final step is compare the predicted response variable values against the observed, the actual response variables, and see how close they are. So the difference between the two is called the test error metric. And your job is to minimize this error. So there's always going to be an error in machine learning. I mean, I think maybe people don't state that strongly enough up front, is that machine learning is probabilistic. So you're never going to get 100% accuracy in your predictions. You just never will. So the goal is to reduce this error between observed or predicted and actual to a point where you can safely say, well, this is highly predictive. It might be 95% right all the time. It's not going to be 100%. And the way that you can achieve this accuracy, I think I mentioned this a while back, is is something that some of the Kaggle masters, the winners of the Kaggle competitions have said what their secret to success was, and it's called clever feature engineering. And that is selecting predictors for the most accurate model. And you can use domain knowledge for choosing predictors, or you can maybe automate the process using a forward and or backward stepwise selection process. It's very iterative, very slow, but if you don't have that many predictors, you can realistically do it. And there's some R packages that help you do the stepwise selection of features. Or you can use what's called an AutoML tool. And an AutoML tool, these are all the rage now too. There's companies that are sprouting up all over the place with like new ideas on how to come up with automated ways of selecting feature variables. And so that's what they do. So this, what I just described to you, is sort of the crux of machine learning. It's very important to understand. Here's a diagram which kind of tries to visualize what I just said verbally on the other slide, in ways of how you can view the data set that you're working with and its constituent parts, the training set and the test set. So the feature variables and the response variable values of the training set, so that's this blue part up here. The Y column is always the response variable. And then these X variables, these are all the predictor variable values. So all of these values, all these blue values, are used collectively to, see, I just got a spam call on my cell phone. Wish there was a way. Well, I do classify that. Whenever I get a spam call, I always block it. Hopefully they'll use that to train their algorithm. So all the blue stuff we used in our training set to train the algorithm to get the coefficients. And then the feature variable, these orange ones, and the red response variable values in the test set are used to check the accuracy of the algorithm, because the algorithm is going to predict these red ones, but these red ones already exist in the test set. So you have actual versus the predicted. So the actual is just usually denoted Y, and then the predicted are denoted Y hat. See that little symbol above the Y here? That's a hat. So you pronounce that Y hat versus Y. So when I say, compare, when I say minimize the error, compare actual versus predicted, there's ways to perform that. And you, the data scientist, an important part of your job is to evaluate the performance of a machine learning algorithm. So there are numeric metrics that you can use for doing that. And there are also data visualization methods. These are called diagnostic plots. So this slide basically talks about metrics, numeric metrics for regression and classification. So the numeric metrics that are popular for regression performance, one is called R-squared, and another is called RMSE, or root mean squared error. So between these two, there's others, but between these two, you have a good sense of how accurate your algorithm is performing. But this only works for regression. If you do classification problem, you have to do something entirely different. You have to calculate a misclassification error rate. Or you can use something called a confusion matrix. Or you can plot what's called a ROC curve, or calculate another metric called AUC, which stands for area under the curve. And then you can plot a ROC curve. And these should tell you how your algorithm is doing. Now, one of the things, sort of a byproduct of this effort here, is one of the things you might find out is that your algorithm is overfit. And that just means that it is too well trained on the training set, so that when you try to generalize the use of the algorithm to the test set and beyond, like new data, it performs poorly, because if it's too well trained for the training set, that means it won't be able to embrace other data that's not in the training set. And so this is a very common problem in machine learning called overfitting. You have to be able to sense when something's overfit. You have to be able to act against it, because if you have an overfit situation, then your algorithm is going to be very poorly predictive. So that's one thing that you might discover at this point. Interesting, I just want to point out to you, there is an R package specifically for this area that we're talking about. It's an R package called ML metrics, and it's a collection of machine learning evaluation metrics. So these are functions you can call, and when you learn how to use them, it will help you down this road. So I would encourage you to research this package. It can be very helpful at this stage. Okay, so let's talk about linear regression, our first machine learning algorithm. So linear regression is based on the assumption of a linear relationship between feature variables, predictors, and the response variable, the value to be predicted. So for linear regression, it's assumed that the response variable is quantitative, continuous, numeric, whatever you want to call it, and the predictors are either quantitative, qualitative, or both. So that's very flexible, what can happen here. So the way the algorithm works is that it uses a known linear mathematical function based on statistics and mathematics to define a line that is used to approximate the unknown function that generates the actual data, the observed data. So if you remember back in high school algebra, where they had you have graph paper and you'd be plotting lines. So you'd have like an equation that would generate the points to appear on a line. That equation, y equals mx plus b. And, where m is the slope, b is the y-intercept, and x is the data on the x-axis. And so if you plot all those points, you get a straight line. So the known function, this line that I'm talking about, is often called the hypothesis function, since it's the one you choose to approximate the actual, albeit unknown, function that generates the actual data. So with linear regression, we assume the unknown function is linear, which it probably isn't, but we're trying to approximate it. And then using the known function, the hypothesis function, we can use data set to fit or train the model by learning the set of coefficients for the hypothesis function. And the most common approach for fitting the model in this way is called ordinary least squares for linear regression. Now, sometimes you cannot approximate this actual unknown function that generates the data. So if you imagine a scatter plot, so x and y, right? And there's a bunch of data points on the plot. Now, the theory is that there's some mathematical function, relating the variable y and the variable x. And this unknown function will generate all the data points, but it could be very, very complex. And that's why I call it the unknown function, because it's so complex that you'll never really know it. But it doesn't matter because you're approximating it anyway. So here's an example of a very complex function. So here's a scatter plot, x and y. And these data points, for some reason, they resemble Homer Simpson. But somewhere in the universe, there is a mathematical function between x and y that actually generates all these, data points, whether it's, his lips, his eyeballs, little strands of hair, whatever. But look at what that function could be. Here's a function. Oh my God. Very complex, right? I don't know for a fact that this function actually generates Homer Simpson, but it just proves the point, is this unknown function, you don't really want to know what it is, because you probably will never ever know it, but it's too complicated anyway. So the better approach is to approximate it. And that's what ordinary least squares does. You can use EDA and data viz techniques to better understand any sort of relationship between the response variable and the predictors. That's one of the reasons why we do EDA and data viz. And so the first thing we'll consider is like a special case of linear regression. It's called simple linear regression, which involves just a single continuous predictor. And then, of course, we have a single continuous response variable. So we have predictor response variable. And we'll be using R's LM function to fit the linear model, and then use the model's model coefficients that were calculated to make predictions. And we'll also use a scatter plot. There's different scatter plots that we're going to see on how to sort of support our understanding of regression. So we're going to look at a scatter plot of the response variable value and the predictor value. And then we'll plot the data points, and then we'll plot a so-called regression line, sometimes known as a line of best fit. And we'll see instantly how the plot will show how far off this regression line the data points are. Because if they're close to the regression line, that means we have a very predictive model. If they're very crazy, like no sense of closeness to the line, that means maybe the model won't be that predictive. Because what we'll be measuring here is the actual data points versus the regression line, which are the predicted data points. And then multiple regression. I mean, you can get a lot of work done with just simple linear regression, but it's only able to make predictions based on a single continuous feature variable. But real life problems, you probably need more than one predictor. So multiple linear regression uses multiple feature variables. But the good thing is we can use the same ordinary least squares approach that we used in simple regression. We find the coefficients for the hypothesis function. And just for your knowledge, this is done by minimizing the sum of squared residuals. Residual, you're going to hear that term a lot. It's just the difference between actual and predicted. So if you try to minimize that gap, then you're going to be doing a better job with this type of machine learning. So we're going to be using the LM algorithm in R once again to find multiple least squares regression coefficient estimates. And R can easily handle multiple linear regression by computing the same linear model data encountered in the simple regression case. So it's not a big leap for the algorithm to go from simple to multiple. So as we're going to see in machine learning, there's every algorithm has its own set of diagnostic plots. So these are plots, visualizations that the algorithm produces to help you debug the algorithm. So that's very nice. The algorithm helps you debug the algorithm. So with linear regression, R's LM algorithm offers 4 diagnostic plots. Each one has its own way of looking at the health of, the predictive accuracy of the algorithm. So let me go through the 4 diagnostic plots and highlight what you should be looking for. So in the next 4 slides, I'm going to show you a good plot and a bad plot. And so the good plot's always on the left, and the bad plot's always on the right. And what I mean is a good plot indicates a healthy regression model. And the bad plot indicates a regression model that is not going to be very predictive. So what we're looking at now is what's called a residuals versus fitted plot. And it's used to check the linear relationship assumptions of the model. That's at a high level. So the x-axis shows the fitted or predicted response variable values. The term fitted is the same as predicted. And the y-axis shows the difference between actual and predicted value. So that's the residual value. And so these diagnostic plots, you'll see, I don't know if the color comes through on the screen here, but there's a red line that flows through this this plot, on actually both plots. And a red line should be horizontal. That's what you're hoping for. And you're also hoping that it has no distinct patterns, because that will indicate a linear relationship, which is good. So ideally, the residual plot will show no patterns. So that is, the line should be approximately horizontal at the zero point. Here's a 0 point in the plot. And the presence of any pattern may indicate a problem with some aspect of your linear model. So in the examples, the left side doesn't show any distinctive pattern. That's good. But the right side shows that, like this red line here, it's in the shape of a parabola or a second order polynomial, where the nonlinear relationship was not explained by the model and was left out in the residuals. And so this is not a good situation. So if you see something like this on the left, you'll know that it's safe to proceed. So this next plot is called the normal QQ plot. We've seen a QQ plot, quantile plot, before in week 7. So and week 8. So this is a way to show if residuals are normally distributed. So the residual between the error between actual and predicted, do the residuals follow a straight line well, or do they deviate severely? So it's good if the residuals are aligned well on an upward sloping diagonal line. So on the right side here, this one's of concern because these points deviate from this straight diagonal line, whereas the left one is not of concern because all the data points are hugging the diagonal line fairly closely. There is one issue, or a couple of issues, maybe 3 issues here. It will show, and this is kind of a nice tool, is the diagnostic plots will identify observations that might be of concern. So they're labeled here, like row 38 in the training set. Looks like row 98, row 36. These are rows that maybe you should research, see if they're correct, if they represent any sort of outlier or whatever, and then move on. This one, so this is a good one though. This is a very good QQ plot. This one, not so much. So again, you should be hoping for something on the left here so you can move forward. The third plot is called the scale location plot, and it shows if residuals are spread equally along the range of predictors. So the plot is used to check the assumption of equal variance of the residuals. So it's a statistical condition known as homeoskedasticity, mouthful, which is desirable. It's good if you see a horizontal red line with equally, that is, randomly spread out points. The reverse, not desirable condition, is called heteroskedasticity. And a possible solution to reduce this condition is to use what's called a log or square root transformation of the response variable. I've had to do this on occasion. So instead of plotting or using, the response variable in the regression model, you use a transformation. You use a log or square root version of the response variable value, and then that's your response variable, the functionized version of it. So in the samples here, the left side, the residuals appear sort of randomly spread above and below the horizontal line, which is good. On the right side, though, the residuals appear to spread wider along the x-axis as it passes around the x-axis value of 5, sort of spreads out. And because the residuals spread wider and wider, the red smooth line is definitely not horizontal. It's at a steep angle. So this one, it's on the left is not perfectly horizontal, but it's typically what you will see and what you will be happy to see. This is not good on the right side. Okay, the final plot is called the residuals versus leverage plot. And it helps find what are called influential observations, if any. Influential observations are different from outliers. You can have both in a data set. So not all outliers are influential in terms of linear regression. So even though the data might have extreme values, they might not be influential in determining a regression line. So this means the result wouldn't be much different if we either include or exclude them from the analysis. So they follow the trend in the majority of observations that don't really matter, which means they are not influential. On the other hand, some observations could be very influential, even if they look to be within like a reasonable range of values. They could be extreme observations against a regression line, and they can alter the results if we exclude them from analysis. In other words, they don't get along with the trend in the majority of the observations. So unlike the other residual plots, this time, like any sort of patterns you might see, it's not really relevant. But what you need to watch out for are outlying values at the upper right corner and the lower right corner of the plot. That's where your eyes will be focused. Upper right, upper right, lower right. Those are the places where cases can be influential against the regression line. And so what you're looking for here are observations outside of what's called the Cook's distance area, which is represented by a red, by a dashed line. So when observations are outside the Cook's distance area, meaning they have a high Cook's distance score, the observations are influential to the regression results. And the regression results may be altered significantly if we exclude those cases. So, for example, the left side is sort of typical what you see when there's no influential observation. Like you can barely see like these dashed lines, like down at the bottom here, and there's nothing up at the top. And this is a good situation where your Cook's distance is like really on the extremities. But on the right side, you see the Cook's distance lines hanging low here and rising high up down here. And you see like this observation here, it's labeled with 49. That's a row in the training set. So the plot identified this as an influential observation. So if you saw this and you, let's say, just excluded the 49 observation from the analysis, you just like temporarily removed it or whatever, the slope coefficient in this example changes from 2.14 to 2.6, and the R-squared metric goes from 0.75 to 0.85. So those are pretty big impacts on the regression analysis. So bottom line is you should take this indication here and carefully look to see what's going on with this observation 49 so that you can feel free to move forward. So all these plots are things that you look at when you are evaluating a regression model. This slide is just sort of a summary of other statistical metrics for evaluating predictive performance. I mean, we talk about R squared, but there's other F statistic, T statistic, all these things. And you can look these up in pretty much any statistical textbook. And so you can see that there's a number of statistical measures that you can use for regression. In class, we are going to be looking at RMSE and R squared, but there are others, as you can see. So now let's talk about classification. So everything I told you about regression and the metrics and diagnostic plots, just that does not apply to classification. You have to learn totally different techniques. So classification with the logistic regression algorithm is applied when you have a binary or two-class categorical response variable and one or more predictors. You use the GLM algorithm in base R for doing logistic regression. GLM stands for generalized linear models, and there's actually other work that GLM can do, but we're going to configure it to use for use with logistic regression. Let's see, so with classification problems, you go through the same process of dividing the data set. into training and test. So use the trained model to make predictions on the test set. But logistic regression does something you might consider unusual, is that when it doesn't make predictions outright, it offers probabilities of class membership. So it will say, oh, for these, categorical response variable values, it can only offer that, yeah, this is like 60% likely to be this class. This is 95% probability to be this class. So it's nothing definitive. It's probabilistic. So what you have to do if you're using this algorithm is you have to use these class membership probabilities and pick out a cutoff or a threshold value that may be correct, maybe not. You have to experiment. So you might use let's say you were using logistic regression for predicting spam emails. Okay, so you could use a predicted threshold probability of 75%. So that is, if this algorithm is looking at all the details of these emails, like the subject line and the from email, and then the body of the text and so forth. These are the data points, and it comes to the conclusion that this email is 70, or let's say 60% likely to be spam, but your threshold is set at 75, then that email is going to go in your inbox. Whereas if you have an email that it says, oh, I'm pretty confident it's 95% likely to be spam, and your threshold is set at 75, it's way above the 75. So this email is going to go straight to your spam folder. And you can play around with the accuracy of that, because remember, you have the actual response variable values and the probabilities of the predicted response variable values, and you can do some sort of comparison. And this is the kind of thing you're going to have to do on homework 3. So that's important. The next algorithm we're gonna look at is called random forest. So random forest you can use on a multi-class categorical response variable value and one or more predictors. So it's more flexible than logistic regression. This is not part of BaseR. You have to download this package called random forest. And then the algorithm itself is called random forest. And as before, you split the data set into training and test, use the training set to train the model, you get the coefficients, and then you use them to make predictions on the test set. And one thing of note here is that random forest can also be used for regression problems. Now that's interesting. It's because random forest is based on decision trees. And so it just means that your response variable when using random forest can be numeric, continuous value. So this seems to say that you can use it for anything, including what you normally would use for regression. And that's exactly what we're going to do on the class project, is we're going to use random forest on a numeric response variable value. Because the thing in the class project that you're trying to predict is numeric. And so we're going to use random forest for that purpose. Now it turns out there's like over 20 implementations of random forest in R. So if you click on this link, you can go to a list, and they all have their pros and cons. But for our purposes, we're going to use the original one that's been in R for ages. It's not the fastest algorithm in the world. In fact, when you go to train the random forest for the class project, you may get excited and worry that you run this random forest algorithm on the training set and nothing happens. You're going, oh no, what did I do? No, it's just taking a long time. And depending on the speed of your machine, it could take 5-10 minutes to complete the training. So be patient, go get some coffee or something. But it's not broken. It just takes a while. There's other implementations that are faster. So maybe at some point you can choose to try some of these other ones out. But this note here is important about being able to use random forest for regression problems, because my recommendation for you is, after this class is done, just spend some time really learning a lot about random forest. I mean, there's so many resources to learn about, how it really works. Like there's a whole chapter in the ISL book on random forest, tree-based methods. And the reason you should invest your time doing this is because you can use random forest for everything that you might want to do for the next year or so. It's perfectly respectable to use random forest. Now there are other, more powerful, sexier algorithms out there, like XGBoost is all the rage, Cat Boost, there's all these boosting algorithms, but they're more complicated. And I would say just hunker down and learn about random forest. Learn everything you can, and just use it for everything. And once you get good at it, then you can branch out to other things. Now, one thing I want to mention about these algorithms is that, and this is one of the reasons I really love R, is because the way you specify the response variable and the predictors in R is very intuitive. Remember back when we were playing with box plots and we were saying, I want to show this variable with respect to another variable, and we had the little tilde, little squiggle symbol. Well, that's called a formula notation, and that is exactly what you pass to a machine learning algorithm. And we'll see that in the next video when I talk about the code. So on the left side, that's the response variable, and then you have the little tilde, and then you list all the predictors on the right side. So simple. Well, other languages don't work that way. Okay, other languages force you to specify a vector with all your response variable values, and then a data frame with all of your predictor values. So like two separate pieces. So you can use random forest that way. It will, if you use the argument X, the argument Y, you can specify for Y, the vector response variable values, and for X, the data frame of predictor values. Split them up. And so that is how I'm asking you to do it for the class project, just to get you experience in doing it the way other languages, like Python, you do it that way. And I want you to get experience doing it that way in R, because you should have all the tools where splitting it up that way shouldn't be a big deal. Okay. So with classification, here are the ways you assess how well it's predicting. You plot, well, you calculate an AUC ROC curve. That's the performance measurement for classification problems. So you calculate the AUC, which is a numeric metric. And it AUC stands for area under the curve. And what you're doing there is really just integral calculus. That's what integral calculus is. It's just determining the area under the curve. So that's very widely known. Then the ROC stands for receiver operating characteristics, is like an old technique that was developed back in World War II in the military. And it sort of, the term has carried forward to this day. It's kind of weird, but people just call it ROC curves. It's a probability curve. AUC represents the degree or measure of separability between the classes. And what that means is that, does your algorithm sufficiently distinguish between the two classes, or in our case, levels in a factor variable for classification? Or is it kind of muddled and you can't really tell one between the two? So based on these two, measures, one is metric, one is visual, you can have a pretty good idea of how your classification problem is functioning. So the higher the AUC value, the better the model is at making predictions. And then the ROC curve is plotted in a very standard way. On one axis, it's the TPR, true positive rate, against, on the other axis is the false positive rate. TPR is on the Y, FPR is on the X-axis. And so, so it's just a matter of like calculating these numbers. So here are these very simple formulas. So if you want to calculate the TPR, which is also called recall, also called sensitivity, you total up all the true positives and divide it by true positives plus false negatives. So when we talk about true positive, false negative, what does that mean? Is when you're looking at the actual versus predicted values. So the actual values in the test set, the actual response variable values in the test set, and the predicted values produced by the algorithm, you can compare the two. And if the algorithm predicted the same as the actual value, then that's a true positive. And there's a lot of combinations of these things, as we're going to see in a table in a minute. So if you total up all these values, you come up with the TPR values, and then FPR is the other axis in our ROC curve, is 1 minus specificity, okay, where specificity is defined by this little formula here. So not very complicated, just takes some tabulation efforts. So here's what a ROC curve looks like. And this is an example of a very good ROC curve. So here's our FPR on the X, our TPR on the Y, and that's the data we're plotting. And if you have a curve of these values that look like this, where the curve goes way up, almost to the corner here and then tapers off, this is considered a very good ROC curve. This is what you want a ROC curve to look like. And then the area, this green area under the curve, AUC, is the numeric metric, and you want that to be as high as possible. See, so the greatest area under the curve as possible. Now, if you had a very poor ROC curve, let's say it's this dashed line, that means the algorithm doesn't do a very good job at predicting. It's half the time it's correct and half the time it's wrong. So it's like flipping a coin. So it's bad. So if you get like a curve, a ROC curve that maybe doesn't go quite as high, maybe sort of tapers off early on, it might still be good. Okay, but it's not. This is a very good, a well-structured ROC curve. This is what you want. So when we look at the code, I'm going to show you some actual data generated ROC curves, so you can see what we see in reality. Oh, one thing I should say, this has been normalized to 100. Normally, AUC values are from 0 to 1, but this has been multiplied by 100, so that's why it looks like that. So the other way you can assess, let's see, we only have 2 more slides, so we're almost done. So the other way we can assess the health of a classification problem is by building a confusion matrix. And in R, we have a perfect function for doing this. It's called table. It's a table function. And so we're going to see an example of a table function. But basically, a confusion matrix is calculated using the predictions of a classification model on a data set. By looking at a confusion matrix, you can gain better understanding of the strengths and weaknesses of your model. You can better compare the two alternatives of models to better understand which is better for your applications. You might do one experiment and you produce a confusion matrix, then you do another experiment that's slightly different, and you have a different confusion matrix, and you compare in order to tell you which model is better. So it's also a very useful way of assessing the success of a model. So the columns labeled actually positive, actually negative, refer to ground truth labels in your data set. That is, if you were trying to identify, let's say, handwritten digits, like image classification, whether the digit is truly a 1 or a 0, or whether a patient was truly diagnosed with a disease, 1 or 0, whether an email is spam or not 0, 1 or 0. And then the rows in a confusion matrix are labeled predicted positive, predicted negative. And those refer to your model's predictions. Like what does your model think the label is? So this confusion matrix encapsulates actuals and predicted. And it has the values. The values are in the boxes of the table. So true positives, the number of positive examples that the model correctly identified as positive. True negatives, the number of negative examples the model correctly classified as negative. False positives, the number of negative examples the model incorrectly classified as positive. That is, the negative examples that were falsely classified as positive. And then, finally, false negatives, the number of positive examples that the model incorrectly classified as negative. That is, the positive examples that were falsely classified as negative. So, this is like a sum total of all your assessment for the model. And so here's like an example of that. So this was based on, let's say, an actual data experiment. I guess it has to do with maybe some sort of construction industry application. So the ground truth or actual is labeled at the top. The predicted values are labeled at the side. What you're hoping in a confusion matrix like this is that all of the values will appear along this diagonal, which is colored here. So if most of the numbers, the biggest numbers, appear along the diagonal, that means that the algorithm is predicting what the actual value is in the test set. So like here, this first one, for 2,385 observations, the algorithm predicted asphalt, and it really was asphalt. Whereas, like say here, it predicted asphalt, but 4 times it was actually concrete. So it was wrong. So any values that you see in the upper or lower triangles here are incorrect predictions. So you want to see fewer totals here. And that's pretty much the case in this example. You have 4, a 4, here's an 8 and a 9. Here's the biggest count of errors is 12 down here. But all told, compared to 68, almost 7,000 observations, the errors don't amount to much. So, like I said, you're not going to ever get complete predictive accuracy. It's not going to be 100%. Even our little toy data sets, we're going to see you don't get 100%. You get close, but not 100. But certainly for a real life data set, it's not going to be 100%. So this is reality. This is reality. Okay, so here's our code module that we're going to be considering later. We're going to have code for regression, simple and multiple. We're going to have code for logistic regression. We're going to have code for rock curves, and then we're going to have code for random forest. And yeah, that's That's what we still have to do. But I'm going to call it for tonight because my voice is fading. So still the effects, I'm afraid. And so we will, I'll make this recording available to the rest of the class who didn't make it tonight. And feel free to revisit the recording whenever you please. And then I will schedule a follow-up Zoom for just the code part of the lecture for tonight. I'm thinking it's probably another hour and a half for the code. So and then I'll make that recording available too. So thank you for visiting tonight, and we'll see you again on Zoom, and we'll see you again in person next